Remember optimization from functions of a single variable. There we had this result, Fermat's theorem, that said that a maximum or a minimum only occurs at a critical number. A critical number was a number at which the derivative was either 0 or undefined. We have the same idea for functions of more than one variable. So we call the point x0, y0 a critical point. Now it's a point because it has more than one coordinate. We call it a critical point for the function f of xy. If, well, we want all of the derivatives of f of xy, or in other words, the gradient of f of xy, to either be the 0 vector or the gradient of f of xy to be undefined at x0, y0. So let's maybe look at an example or two of this. Let's say we've got the function f of xy is 2x squared plus 2xy plus y squared plus 2x and minus 3. And we go through and take our, we want to find our critical numbers for this, so or critical points. So what we'll do is we'll take the gradient. The gradient of this function first is the partial derivative with respect to x. So that's 4x plus 2y plus 2. We need that derivative to be 0. This is the partial with respect to x. We also need the partial with respect to y to be 0. So that's going to give us 2x plus 2y equals 0. And now, conveniently, this is a system of linear equations. Right, we can divide the first equation by x, and that's going to give or by 2, and then it'll give us 2x plus y equals -1. And the second equation, x plus y equals 0. And then we can solve this by matrix methods. So we can translate this into the system 2, 1, -1, 1, 1, 0. And then we can solve this by multiplying the second row, by switching the two rows first. So that'll give us 1, 1, 0. And then we multiply the second row by -2 and add it to the first. So -2 plus 2 is 0. -2 plus 1 is -1. And 0 plus -1 is -1. Now we can add the bottom row to the top row and multiply the bottom row by -1. So this tells us x equals -1, y equals 1. So this gives us a point, -1, 1. This is the critical point for this function of two variables. And maximums and minimums can only occur at critical points. So along those lines, we don't know if this critical point is a maximum or a minimum. So this is where the second partial derivative test comes in. So just like in functions of one variable, we had the second derivative tests, whereas if you recall, if the second derivative is positive, our function is concave up, so that must be a minimum. And if the second derivative is negative, our function is concave down, so that critical point must be a maximum. We have the same idea with the second partials test. But here you sort of have to look at two different directions at the same time. So what we do is we define this this matrix H, and this is the matrix of second partial derivatives. So we look at the second partial with respect to x, fxy, fyx, and fyy. And we go through and take the determinant of this matrix. So one of three things will happen. If H is positive, then I know that we have an actual maximum or a minimum. If H is negative, that says we have what's called a saddle point. And that means it's not a maximum or minimum. And if H is 0, this test is inconclusive. So let's maybe look at an example of each of these. Let's for our first, let's say we've got this function f of xy. We'll do something that's nice and easy, x squared plus y squared. So first we go through, take the gradient. So we get 2x, 2y, and this has to be equal to 0. So this is a fairly easy system to solve. We go through and divide the first equation by x, by 2, and we get x equals 0. We take the second component, we divide that by 2, and we get that y is 0. So our only critical number is 0, 0. Now let's go through and look at the second partials test. So h is then the determinant of, we take the partial with respect to x, is 2x. Take its partial with respect to x, and that's 2. We look at, next we do the mixed partial. We take the partial with respect to x, which is 2x, then take its partial with respect to y, which is 0. And then by equality of mixed partials, I know this is also 0. And then finally the second partial with respect to y is also 2. And so this gives us 4 minus 0, or 4. So we know that this is a maximum or a minimum. I haven't said one way or the other whether it is a max or a min. I don't know which it is yet, but I know that this is an extreme point. And the way we test this is we look at just the first entry in the matrix. If this is positive, this sort of leads us back into this scenario here. If it's positive, we know that the function is concave up. So this must be a maximum. And you can actually look at either of these two corner partials here. You can either look at the xx or yy, and they'll both, in order for this to be positive, they must both be pointing in the same direction. So this tells us that we've got a max here. Let's look at another one. Let's say we've got f of xy is x squared minus y squared. So we go through and take our gradient. So the partial with respect to x is 2x. The partial with respect to y is negative 2y. And we need this to be 0, 0. We need both partial derivatives to be 0. And this tells us that x is 0 if we solve the first component equation, and y is 0. So we've got the same critical number, 0, 0. If we go through and do the second partials test here, the second partial with respect to x is 2. The mixed partial with respect to x and then y is 0. Y and then x is also 0. The second partial with respect to y is negative 2. We take the determinant here and we get negative 4. And that says this is a saddle point. So that means this is not a max or a minimum. So what that means geometrically, if we were to sketch out what this saddle point is, that says if we look at it from the x direction, if this is the x-axis and this is the z-axis, the function looks like a minimum. Whereas if we look at it, if we change our point of view and look at the y and the z-axis, it actually looks like a maximum. So depending on the direction of approach, it looks like a maximum coming in along the x-axis, but a minimum coming along the y-axis. So it's neither. We can trace either direction and come in along a max or a min. Let's maybe look at an example that that comes up inconclusive, just to make sure we've seen one of each. Let's say we've got the function f of xy is x squared y squared. So we're going to go through and do the same thing we did before. First up, we take its gradient. The gradient of f, the partial with respect to x, is 2x y squared. The partial with respect to y is 2x squared y. And this must be 0, 0. So here, we actually, in order for both of these components to be 0, either x is 0 or y is 0. In order for the first component to be 0, one of the two coordinates has to be 0. In order for the y component to be 0, either the x or the y has to be 0. So we're in this funny case here where x is 0 or y is 0. So in other words, we've got an infinite number of critical points here. If we were to look at this from above, the x-axis and the y-axis, along the x-axis and the y-axis, along the x-axis the y is 0, so every point along here is a critical number. And again, if we look along the y-axis, every point along here, the x-coordinate is 0. So all of these are critical points. We have an infinite number of critical points on this. So let's see if we can make heads or tails of that on this, on the second partials test. So we go through and take our second order partials. So let's actually take a little time to expand this out. So we know that fx is 2xy squared. fxx is 2y squared. If we look at fxy, This is the partial of x with respect to y is 4xy. And if we go through and look at fy, this is going to be 2x squared y. Just go through, take the derivative. Fyy, we take another partial with respect to y, we get 2x squared. And fyx, we take the partial with respect to x and get 4xy. Okay, so let's now form that matrix H. So this is fxx, so this is 2y squared. And then the mixed partials, 4xy. And then again we have the mixed partials, 4xy, and then 2x squared. So we go through and take this, we cross multiply here, and along this entry here we've got 4x squared y squared minus, we take the other diagonal, and we've got 16x squared y squared. So we go through and subtract these out, and this is going to give us negative 12x squared y squared. So this looks like it's going to be negative, but remember, along any of these critical points, x must be 0 or y must be 0. So no matter what critical point we're on, if we plug in x equals 0, this gives us 0. If we plug in y equals 0, this gives us 0. So this is 0 at any critical number. Well, that says that this test comes up inconclusive. I don't know if it's a max or a minimum. So we've got to do something else to determine whether or not we have a max or a min. Now we're actually going to just look at the function in the first place. Okay, so f of xy was x squared y squared. And at any critical point, right, those critical points we discovered previously, x was 0 or y was 0. That was our family of critical points in there. If you plug x equals 0 or y equals 0 into the original function, the function is going to be 0. Okay, well, what if we plug in something that isn't a critical point? If you plug in any non-zero number for x, that's positive. And if you plug in any non-zero number for y, that's also positive. So, at any other point, f of xy is positive, which is going to be greater than 0. That means that this collection of critical points that we found were actually minimums. Every one of them came out to be 0, and every other point comes out to be greater than 0. So that means f of any critical point on this particular problem turned out to be the minimum, or 0. Now this is kind of a fluke, this doesn't always happen, but those are the three cases we can fall into for the second partials test.